In this video, we're given a separable differential equation, and we're asked to compute the general solution. So what we want to do here is explicitly solve for y as a function of x that satisfies this equation. General solutions come with the flexibility of an arbitrary constant, and the way you nail that down is in part B. I'm given an initial condition, so y of 0 is equal to 2. That will allow us to determine the arbitrary constant and write down the particular solution. That's a solution to the differential equation that satisfies the initial condition. So the approach to an equation like this is to just gather all the y dependence on one side, all the x dependence on the other, and then we're going to integrate. And the integral on the left side is easy. That just integrates to 1/3 y cubed. But the integral on the right side, that's a classic integration by parts integral. So we let u equal x, and the point there is that when we differentiate x, we arrive at something simpler. So du is just going to be dx because the derivative of x is 1. The other part of the integral is dv. That's an e to the negative x dx. And when we integrate that, we get negative e to the negative x, just using the chain rule backwards there. So on the left side of our equation, we have a 1/3 y cubed. And there should also be a plus c arbitrary constant of integration there. But I'm going to go ahead and wait until I do the last integral in this problem and then put the plus c in. And we apply the integration by parts formula, and I start with a u times v, so that's a negative x e to the negative x, minus the integral of v du. Well, v is carrying a minus sign, so I'm going to put that out in front, and du is just dx. And now we just have to take the integral of e to the negative x, which gives us another negative e to the negative x. And here's where I'll make sure to put in my plus c. Now, just to clarify, both integrals here produced a plus c, but when you combine two arbitrary constants, you just get another arbitrary constant. And now what we're looking at is the general solution to the differential equation, but it's written in implicit form right now. I would like to actually solve for y here. So I multiply both sides by 3, and I get negative 3x e to the negative x minus 3 times e to the negative x. And then I get 3 times an arbitrary constant, but that's just some new arbitrary constant, so I'm just going to write a plus c. Finally, I take the cubed root of both sides, or I could write it as a 1/3 power, and I have my explicit solution. So there's the function y of x that satisfies the original differential equation. Now we want to nail down what specific function is going to satisfy the differential equation, but also pass through the point 0, 2. So when I replace x with 0, I should get y equals 2, and we just go to our general solution and sub those values in. So I get y is equal to 2. When x is equal to 0, and when I plug in 0 to the first term, that vanishes. In the second term, e to the 0 is going to give me 1, so I end up with a negative 3 in there. And I have a plus c, and the whole thing raised to the 1/3 power. So we cube both sides, and I end up with 8 equals negative 3 plus c. And this means c is equal to 11. Then we're going to substitute c equals 11 into the general solution, and we have our particular solution. So we call that yp of x. That's negative 3x e to the negative x minus 3 e to the negative x plus c, so plus 11 in there. And now we have the function of x that both satisfies the differential equation and passes through that specific point that we wanted it to pass through, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.